Continuing on what we were talking earlier, now let's try to model the other remaining constraints of the problem. Okay. So now we will try to write the analogous composition constraints, analogous composition constraints for nitrogen, sulfur and phosphorus. Okay. Please do this as a homework, but I will I'll show you one more, basically how to write the case of nitrogen. So if we go back in the previous table, we can see that the percentage of nitrogen falls in this row. Okay. So if we use this, we can write this constraint as follows. Okay. We will write it as same way, 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4. Okay. The first 4 are zeros, if you can see this, these first 4 are zeros, then you have a 90, 96 and a 0. Okay. So then it's in percentages, we are talking about is plus 0.9 times x5 plus 0.96 times x6 plus 0 times x7. Okay. If you think about the previous case, this is exactly how we went through the previous case. Remember this scenario where we wrote the constraints for each one, x2, x3, x4, we wrote it exactly the same fashion. Okay. Now we can see that this will go to 0, this will go to 0, this will go to 0, this will go to 0 and this will also go to 0. So our constraint will be 0.9 x5 plus 0.96 times x6. Okay. That is our constraints ideally in this case. Okay. Now because of weight percentage, because of percentage of nitrogen, we divide by the total fertilizer. Okay. So which implies 0.9 x5 plus 0.96 x6 divided by x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7, okay, whole thing multiplied by 100. Okay. So remember this, the same fashion, the same constraint is what we are trying to do at this point. Then we multiply this into the scenario which will give us 90 x5 plus 96 x6 divided by x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7. And we know that percentage of nitrogen should be between what is it, 0.3 percentage to 0.5 percentage. So this will give us 0.3 less than or equal to 90 x5 plus 96 x6 divided by x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 less than or equal to 0.5. Okay. Similarly, we can do it for sulfur. Okay. Percentage of sulfur should be between 0 percentage to as per the question VT should be 0.05 percentage. Percentage of phosphorus should be between 0 percentage to 0.04 percentage. Okay. So these two can also be write like the other two constraints. Okay. So, here we are going to, so same way as we wrote the, so this is the nitrogen constraint, and the one before that is the, this is our carbon constraint, and now we have to similarly write the sulfur constraint and the phosphorus constraint. Okay. So, then we will have all the constraints on the composition of the item. Now, with that, the next aspect of us, or the next thing we need to do is the modeling of the objective function. Okay. So, because the constraints are all modeled now, since this problem involves finding the least cost combination of raw materials, least cost combination of raw materials that meet the demand, that fulfills the demand for 50 kg of fertilizer, of biofertilizer. Okay. So, what we are saying is that the problem involves finding the least cost of combination. How can you combine the raw materials in the least cost fashion, so that we can fulfill the demand of the 50 kilogram fertilizer. Okay. Because of this, the objective function should be simply the cost of raw materials used. The cost of raw materials used. Okay. So, how can we write the cost of raw materials? Where do we get the cost of raw materials? The cost of the raw materials per kilogram is given right here. Okay. This is the cost of raw materials. Okay. So, if that is the case, how do we write that then? We have again x1, x2, x3 are the same way. So, your cost is equal to, if you look in the table, it is, the first one is 200. So, is like 200 x1 plus 250 x2 plus 150 x3 plus 220 x4 plus 300 x5, then plus 310 x6 plus 165 x7. Okay. So, this is the cost of the raw materials. So, depending upon the quantity that you are using, which are given by x1, x2, x3, x4, etc., the quantity that you are using. Okay. So, which implies where each raw material contributes its own cost to the total, So, what we are saying is, if we use 10 units of X7, then the cost will be 165 times 10. Okay. So, you will get to see that this factor will put into this. Okay. Then the optimization goal of this problem, is to minimize the objective, or minimize the cost function over all choices of variables that satisfy the modeled constraints. Model constraints. So what we are saying is that our optimization goal is to minimize the cost function, where the choice of variables, the values of x1, x2, x3, etc. that we choose should satisfy the model constraints. So then we can write it as minimize, okay, 200 x1 plus 250 x2 plus 150 x3 plus 220 x4 plus 300 x5 plus 310 x6 plus 165 x7. We are trying to minimize this subjected to, you are subjecting to our constraints, where we will say that 0 less than or equal to x1 less than or equal to, I don't remember what that quantity was, but the quantity was, I think it was, so if you go back it will be 40, okay. So we will write it as 40, and like this all our constraints will be written here, and finally we will have the, then we will have the percentage carbon constraint, then we will have the percentage nitrogen constraint, percentage sulfur and percentage phosphorus constraints, all of these. So all of these, the choices of variables that fulfill these constraints, then pick the minimum from it. Okay, that is the idea. Okay, I hope you guys understand the how the objective function has been modeled in this case. All right. So now about the solution. Okay, and we are not going to sit and spend time on solving the problem, but we are going to have some thought process on how this problem is to be solved. Okay, so let's think about the problem. Let's do some thinking. Let's do some thinking about the problem. To get insight about a solution. So let's think about the problem. Let's do some thinking so that we can get some insight about the problem. Okay. For example, the objective function is to be minimized. The objective function is to be minimized. And can be achieved whenever the value of any variable decreases. Okay. So the one way to get to the minimal value, can minimize this objective function if we can minimize the value of the variable. So what we are saying here is, when any of these values of these variables, these x1, x2, x3, x4, etc., when these values can be reduced, okay, then you can also achieve the minimization of the objective function. Okay. Or in another way to think about it is, or the smallest coefficients, or let's say, or the variables having the smallest coefficients will be the smallest contributors towards the cost. So what we are saying is that the variable that has the smallest coefficients will also be the smallest contributors to the cost. Okay, and the cost implies per unit cost of raw material. Okay. So if you look into the function, you can see that whoever has the lowest coefficient of whichever variable has the lowest coefficient, it will be the lowest contributor to this. Okay. So for objective function, if we write it down, then we can see that, okay, in this the lowest, this is the lowest coefficient. Okay. So then that means the any value of x3 you put it in will result in the lowest contribution towards the cost, right. So if then if we ignore the composition constraints for the time being, composition constraints, they are the carbon, nitrogen, sulfur, phosphorus. Okay. If you ignore these composition constraints, okay, if you are not working into that, then the manufacturer should produce exactly 50 kilogram of fertilizer from the cheapest raw material, So if the composition constraint is not there, if you are not worried about the carbon, nitrogen, sulfur, phosphorus, etc., then what the manufacturer should do, should produce exactly 50 kilograms of the fertilizer from the cheapest raw material. Okay, and this means 50 kilograms of fertilizer from the cheapest raw material which is worm meal at 150 rupees per kilogram and 60 kg of it is available. How do I know that? Okay, if you go back to the table, you will see that the price of it is 150 rupees and there is 60 kilograms of it available. So I can easily make 50 kilograms of fertilizer from that. Okay, so what are we trying to say is that then the cost will be 50 kilograms multiplied by 150 rupees per kilogram, okay, which will be the cost of the worm meal. So that will be equal to 7,500 rupees. So this is the cheapest I can make this 50 kilograms of this fertilizer. Okay, if we look carefully, or if you think carefully, one cannot do any better than this value. Okay, you cannot produce than this value, which means you cannot produce any fertilizer, any 50 kilograms of this fertilizer at a cheaper price than this. It is that way. Okay, value. This also implies that if composition constraints are enforced, then the possible cost will be greater than 7,500 rupees. Okay, which means you cannot do any lower than this 7,500 rupees. makes it the lower bound. Okay. So, lower bound is that value for which you cannot do any lower, any cheaper than this particular, or you cannot have a solution to this problem any lower than any below this value, or this is the lowest value, lowest value the objective function can take. Okay. So, that is what we are talking about, the lower bound. So, when somebody says a lower bound to the objective function, this is what we talk about as a lower bound. The lowest possible value the objective function can take for a given set of values for the problem. And this value is only feasible, this approach is only feasible if we do not enforce the composition constraints. So, if you enforce the composition constraints, if the composition constraints are enforced, then you cannot do any better than this 7500. So, the lowest possible thing that you should be able to aim at is 7500 rupees per 50 kilogram bag of the fertilizer. Okay. Now, let us take the look at the other side of the problem. Okay. What will be the worst you can do? What will be the maximum? What will be the maximum or worst cost one can do? So, now we saw what is the minimum or the best cost we can do. Now, let us look at what is the worst cost we can do. Okay. So, if you look into this, we have to go back to the data again. If you see this, the most expensive of this is the most expensive. Okay. And there is 30 kilograms of it, and then the next most expensive, and this 20 kilogram of it. If you combine both of these, you can get the most expensive one without violating the composition constraints. So, we can say that use all of, which is 30 kilogram of the most expensive raw material. Okay. That is, what is the most expensive raw material we have? The most expensive raw material is groundnut cake, followed by neem cake. Expensive raw material, rupees 310 per kilogram of groundnut cake. Okay. Use all 30 kilograms of the most expensive raw material, and then the remaining 20 kilograms okay, of the next most expensive raw material, most expensive raw material, that is rupees 300 per kilogram of groundnut of neem cake. Okay. To make 50 kilograms of fertilizer. Okay. So, what we are saying here is, if you combine all of the 30 kilograms of the most expensive raw material, because we only have 30 kilograms of it, which is the groundnut cake, and then the remaining 20 kilograms of the next most expensive raw material, which is 300 per kilogram of neem cake, it will give you the 50 kilogram of fertilizer. This means the maximum realistic cost is 30 multiplied by 310 plus 20 multiplied by 300, which is equal to 9300 plus 6000, which is equal to rupees 15,300. Okay. So, this amount It is the maximum realistic cost you can think about making this fertilizer. This is called as the upper bound. Okay. So, ideally speaking, the optimal solution will lie between the lower bound and the upper bound. Okay. So, the optimal solution always will lie between the lower bound and the upper bound. We seen what's an upper bound and we seen what's a lower bound. Okay. Then to do by yourself. Okay. Then use number 1, use Microsoft Excel to find solution to this problem. Okay. And ensure that optimal value is between 7,500 and 15,300. Okay. If you do all of this by yourself, so you have to use Microsoft Excel. There will be a tutorial. Okay, tutorial will be given in this regard. Okay, you can use this tutorial to find out how to use Microsoft Excel to solve this problem, because Excel have solvers on which you can actually feed this kind of scenarios and it will solve it for you, and ensure that the optimal value is between 7,500 and 15,300. Okay. So, we now know what is a lower bound and what is an upper bound to the problem, and we have also seen how to model a optimization problem using in which the variables are having continuous values rather than the discrete 0, 1 values we did in the first example. And you have seen that we have also fulfilled most of the constraints. Please make sure that these constraints that we are talking about, these composition constraints, should be converted into simplify this. Okay, you can simplify this by basically multiplying it or dividing it throughout. It's easy to make it, and or you can move it into one side. Okay, and then do the simplification aspects of it. So, please go ahead and do that and make this, simplify these constraints. Same way you also have to think about is simplify this constraint. Okay, remember among the 4 laws, one is make it lean, make it clean. Okay, and simplify, can make it linear. So, that is what we are trying to do here. So, simplify these aspects, and with that then try to solve them using the Excel solver. You can find those way to use Excel to solve this problem, made available on many parts of the internet. So, please go ahead and solve this problem, and if you have any questions on this, please let us know in the discussion forum so that we can help you with this regard. And continue learning, continue practicing. The only one way you can do the modeling and of the optimization problems is by just keep on doing it and practice and practice and practice, and that is the only one way you can actually make this actually happen. So, thank you very much for your patient listening. Continue reading and hope to see you soon in the coming aspects of this course. Thank you very much.